So, as I was just saying, I brought a couple of books here just for people to know like what I'm talking about when I'm talking about references for this class. One of the things that you have to get used to in a course like this is that not everything's going to be in one book, because optimal control is a pretty diverse subject. It's been studied for many, many decades, and it's not a subject that has that any one person has really like come up with sort of the unified way of doing it. And so what you'll find is that there are a range of books. Some of them are extremely theoretical. I mean, so theoretical that words don't describe how theoretical they are. There's a really, really theoretical book. I think it's called Optimal Control or Optimal Control Theory by a guy named Vintner. And Vintner's book is just, I mean, he just starts off, he's got everything is just done in painful detail to the point where he's got definition, theorem, proof, definition, theorem, proof. I mean, you sit there and after a while, you're like, where's the optimal control? Because he's like, we define the kth order Frechet derivative, blah, 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 blah. And you're just like, I don't really need to know all this stuff because it's too much detail for an engineering class. Great book for a math course, because that's what they're really interested in, is delving into every last bit of theory. And all you do is prove theorems. That's it. That's the whole class, is proving theorems. Then you've got the other extreme, which is Bryson and Ho's book. Bryson and Ho's book is called Applied Optimal Control. This is a very famous book. It's a book that was originally written in 1975. It might have been earlier than that, or maybe the first printing was 75. Yeah, 75. It was published by Taylor and Francis, and then it was reprinted in its current form, which is I think at Hemisphere Publishing, and then it went back to Taylor and Francis. So this one's back Taylor and Francis again. But this book, the great thing about this book is also the worst thing about this book. The great thing about it is it has tremendous number of examples. It's got so many examples, like you just cannot believe. You just page through this thing, example after example after example after example. I mean, it's just like, oh, examples, right? The problem is that the theory is not presented extremely well in this book, in my opinion. Now, Art Bryson, I don't want to say anything bad about the guy because he's a member of the National Academy of Engineering. He's like, one of the most famous people ever in the history of optimal control, and he's a world-renowned scholar. He's very old now. He's like 85, 86 years old. Very nice, and a very nice man. He never really spent the time in this book to come up with that nice, compact, unified notation which everybody can read really clearly. So you'll find that in the middle of some of his derivations, he just comes up with new symbols, and the new symbols are like, where did he come up with nu and eta and phi? It's like, just like pop, they just come out of nowhere, seemingly. So you have to, like, when you read this book, you need to have a book like this next to it, because if you don't, when you read this book, you'll be like, I have no idea what he's talking about, because so many things are done implicitly through. He'll say, well, if you plug this in here and that in there and this over here and that in there and simplify down, you get this result. That's it. And then you're just like, and you do it yourself, and 12 pages later you'll get that result. So you realize that there's a lot more that you need to get that result than just like going from this line to that line. It's more complicated than that. That being said, some of the examples in here are absolutely indispensable. It's a great book. This is one of the newest books that's been written on optimal control. It's written by a guy named Subramanian Naidu. He's actually a professor at Idaho State. I know him quite well. Really nice guy. And the great thing about this book is this is one thing I love about this book is that he doesn't do everything. But what he does in here, he does very, very well. So you'll see that he doesn't talk a lot about that. He does talk about minimum principle and things, but if you look at the chapters, you'll see that this is a classic example of a book where somebody has taken the time to do something more specific well. He talks about calculus of variations. But he doesn't really go into that much about singular arcs. He talks about linear quadratic control in two different sections, and then he talks about discrete time control. So he covers less material, but it's very elegantly done. The notation is extremely systematic. There's no hand-waving through any of it. He uses the right symbols everywhere, so you know exactly what he's talking about. This is a beautiful book. If you want something, it's a little bit more money. It's not available in paperback. These books are both available in paperback. This book is really inexpensive. If you go buy it from like Amazon.com, you can probably pick it up for $20. This book you won't be able to pick up for that little money. So it's just important to understand that there are options out there for you to learn this material, and you're not going to find everything in any one book. These are just 3 examples of books that I find useful for this material. So when I actually put notes together and when I think about how I'm going to do this, I draw from all these different places because I never get everything in one place. Okay, so that's just for your edification for later on. If you want to see any of these books, by all means, come up and come to my office or something, and we'll talk about them. Today we're going to talk about singular arcs. Okay, this is a kind of a painful subject, but it's an important subject. Singular arcs. And what I'm going to do is, it's one of these things that, in some ways, you have to sort of introduce it qualitatively, and then the best way to actually see how it operates is by actually doing an example. So I have an example in these notes too. Okay. So what we do is suppose we have an optimal control problem. Where on a segment T1 to T2, the optimality conditions provide no information about structure of the optimal control. Such a segment or interval is called a singular interval or a singular arc. It's called a singular interval or a singular arc. The term arc is like a path. It's an arc of a path, right? So now the problem with these are so many optimal control problems have the possibility that the solution lies on a singular arc. Many of these are problems where you have to apply the weak form of the optimality condition. So if you remember that the strong form of the optimal control condition, or the strong form of Pontryagin's minimum principle, is that the partial of h with respect to u is equal to 0. And we can only apply this if the control lies interior to the control set, right? So this is applicable only if u star lies on the interior of the control set. But there's a problem here. We may actually have a situation where the optimal control actually does lie interior to the control set, and we cannot apply this, right? So this is saying that if this condition is applicable, then the control must lie interior to the control set. But it does not say the converse. It does not say just because the control lies interior to the control set that this condition is applicable. All right? It's not an if and only if. So it says that if I can apply dH du equals 0 to get the optimal control, then it must be the case that the control lies interior to the control set. But just because the control lies interior to the control set does not mean I can apply dH du equals 0. The weak form, we have this, which is the general form of Pontryagin's minimum principle, says that the optimal Hamiltonian, or the Hamiltonian applied to x star of t, u star of t, lambda star of t, and t has to be less than or equal to h applied to x star of t, u of t, lambda star of t, and t. It just says that the Hamiltonian is going to be smaller at the optimal control than it will be at any other control. But suppose we have a problem where on the interval t1 to t2 that I referred to here, so suppose now that on t1 to t2, neither of the above conditions yields information about u star of t. So that's a singular arc. So this is a singular arc. It's called a singular arc case. Now, in general, this is why I said this is qualitative, all right? In general, it is not straightforward to determine the optimal control on a singular arc. And the reason it's not straightforward is because we need to know something about the Hamiltonian in order to be able to do this. And so I'm going to follow that up. Because information or key properties of the Hamiltonian must be known. Now, there are certain subsets of problems or classes of problems for which we do actually have some information about the Hamiltonian, and so we're going to restrict ourselves to those cases. But now consider a problem where the Hamiltonian is not an explicit function of time. So what do we know in that case? If the Hamiltonian is not an explicit function of time, what do we know? Yeah, which means what? No, which means what? What's true if the Hamiltonian is not an explicit function? The Hamiltonian is constant, right? So that says that h of x star of t, u star of t, lambda star of t is equal to a constant. Now notice I deleted or dropped the explicit dependence on time because it's not an explicit function of time, right? So in that particular case, we actually can do some things related to singular arcs. So if we look at this, we know that suppose on t1 to t2, h star reveals no information about u star. How is that possible? Well, let's look at it. We know that h is equal to L plus lambda transpose F, right? So if I can't apply dH du equals 0, it means that if I take the derivative of this with respect to u, I don't get any information about the control, right? So that first condition's out. The second possibility is if I apply the minimum principle, which is this over here, or the weaker form, which is this over here, it says that there's no way in the world I could get any information about the control that way either. So what must be the case? So it must be the case that L is not a function of u, or I should say dl du is not a function of u. And the other thing that must be true is that lambda transpose times F is not a function of u. Because, so actually I add one to the, L is not a function of u. I could say, well, let's do it this way. Say neither L nor dl du is a function of u. All right? Because if this isn't a function of u, and this is not a function of u, then the sum of these isn't going to be a function of u either, right? So this whole thing's not a function of u. So if I apply the weak form, I'm not going to get any information about u. Similarly, if anything in here is such that when I take the derivative, I don't get a function of u, I'm not going to get, so this is not a function of u, or d du of lambda transpose f is not a function of u. Now you say to yourself, well, when is that possible? Well, it's possible. And actually, there's some really pathological problems, which are actually practical problems for which this happens. So what we do in that case is as follows, is we say, we know that h star is a constant. But on that arc, we don't have anything that gives us any information about u. So what we do is we take derivatives of h until the lowest derivative possible is a function of u. So what does that mean? So if I take dh dt, d second h dt second, and I keep doing that until I get to some derivative, dqh dtq. We say that we go until the first q minus 1 derivatives are not a function of u. But this derivative, the qth derivative, is a function of u. Now, because this derivative that I've taken, since the original Hamiltonian is constant, it must be the case that dqh dtq has to equal 0, right? Because the original Hamiltonian was a constant, right? So if I differentiate it as many times as I want, every derivative that I differentiate is going to give me something that's going to be 0. And that last derivative is a function of u. So what happens is, when we actually do this, we wind up getting something here that gives us a function of u, and we use that as the condition from which we can actually determine the control. It's singular in the sense that we don't have the information directly from either the strong form or the weak form of the minimum principle. We get it indirectly by having to continue to differentiate on the singular arc. Now, the problem is that there are multiple issues here. First of all, you have to know where the singular arc is, right? So you have to know what time interval the singular arc occurs over. The second thing is you have to know what are the possible conditions, or what is the condition that could lead me to this, the possibility of that singular arc, right? I mean, there has to be something in there that says that if this condition is true, then the solution may lie on a singular arc. So rather than like get into like all of the because this is all very abstract and very theoretical. So what I'm going to do is we're going to do an example, all right? And this was the example I talked about last week. It's a very strange problem, but it's a very practical problem. Well, it was a practical problem at one time. It's not very practical anymore because nobody does this. But you know that. So before I do this, I'm going to go into just a bit of history, just because it's important to understand where these things come from. Back in the 1920s, there was this guy who was a professor at Clark University. If you don't know where Clark University is, it's in Worcester, Massachusetts. Right? And he came up with this crazy notion that if you took a body, which had a lot of mass, and you put it on the ground, and you expelled mass out of it really, really fast, you could propel it to really high altitudes. And he said, well, if you can do this, if you can come up with some sort of a system, a propulsion system, that will just shoot mass out of the back really, really fast. It just burn mass. It'll just go out the back really, really quickly. Then the momentum transfer will take the vehicle in the other direction and make it ascend. And if you can do it fast enough and you have enough of that mass to be able to produce enough thrust, you could propel to very high altitudes and even get yourself out of the atmosphere. Well, people thought he was crazy, right? They said, well, that's never going to happen, right? That's impossible. You can't do that, right? And so he kept on with this thing, and he became kind of a black sheep of the scientific community. This was the 20s and the 30s. And he came up with this problem in 1925 or thereabouts called the maximum ascent of a sounding rocket. So this was the problem. And he said, well, this is the problem. We want to maximize the altitude that a sounding rocket takes to get to, maximize the altitude to get to, for a given amount of mass expended, going in one dimension, vertically upwards. And so the guy's name, it's a great story because, this is like, how kooky scientists, crazy scientists. The guy's name was Robert Goddard. And Robert H. Goddard. And even though he was considered a crazy guy, he stuck to his theory, and he wasn't going to let it go. And after World War II, after he died, of course, this all happens after people die, right? They finally realized the guy's not completely crazy, right? They came up with this, they started thinking about propelling missiles and rockets and putting things into space and everything, and Sputnik came along and all this other stuff. And everyone said, hey, let's look back at Goddard's problem. Goddard did this back in the 1920s. He came up with this concept, right? Well, now he's got a whole NASA Space Flight Center named after him, and the whole story that goes along with it is basically he's considered the father of modern American rocketry because he was so ahead of his time that nobody could possibly envision that this even made any sense whatsoever. So his famous problem is what's now called the Goddard rocket problem, and it goes like this. And it's a really great problem because you would never think that the optimal solution actually looks like this. So here's what it is. It's what's called what I said. It's a one-dimensional ascent of a sounding rocket. If you don't know what a sounding rocket is exactly what it is. It's like, you ever heard the concept of just screaming while something's going really, really fast? Like on a roller coaster? Well, that's a sounding rocket. You just fire, and just keep firing until you don't have any more fuel left to fire, and that's it. You're done, right? Wherever you go, right? So there's not much to it. The problem works like this, is that we want to maximize altitude. At TF, where TF is free. Okay? So the objective function is to maximize altitude, but we do everything in this class with minimization, right? So we have to have it be minus h of TF, because if I'm maximizing altitude, it's the same thing as minimizing its negative, right? So that's the cost function, or the objective function. The dynamics, this is the cost. So it's a Mayer cost problem. The dynamics look like this. If you have a one-dimensional ascent of a rocket, the dynamics are h dot equals v. V dot is equal to t minus d over m minus g. And then the mass flow rate is minus m dot equals minus t over c. The control in this problem is t. So we have a bounded control, which is that the thrust can never be negative, and it goes between some 0 and some T max. Now, if you look at this, you say, well, you got to have some initial conditions. So the boundary conditions are h at 0 equals 0. V at 0 is also equal to 0. You're starting from the ground. And m at 0 is equal to some initial mass. the final time is free, and everything here at the final time is free except for the final mass, which is that m at TF is equal to mf. So you're going to burn a fixed amount of fuel to do this. You're just going to burn until that amount of fuel, until your tank basically goes empty, and then you stop. Okay? So now let's look at this problem in a little bit of detail, because this looks like a pretty easy problem, right? I mean, this doesn't look like really difficult. So a couple of things I want to point out here. D, which is equal to the drag force, is a function of altitude and speed. That's typically what drag is a function of, right? Because drag is a function of dynamic pressure. Dynamic pressure is a function of density. Density is a function of altitude. It's a function of speed because dynamic pressure is a function of speed. It's also a function of speed because the fact that drag is proportional to v squared. So you wind up with it being a function of altitude and speed. Okay, and if you're going in one-dimensional upward, it's not a function of thrust. It's just because thrust is the input. Okay, so now we have this problem where drag is a function of, and all these other things are constant. G is a constant, C is a constant, and M is governed by these dynamics. So let's formulate this optimal control problem. Okay, this is a good example of a simple problem where we can actually get our hands on everything without any weirdness. Right? It's a pretty easy differential equations, right? I mean, the objective function is fairly straightforward. So how are we going to do this? So let's go ahead and do this. This is a great problem, because it really shows you why optimal control theory is so difficult, because this is not a difficult problem. So what do I need to do if I want to formulate the optimality conditions to determine the optimal control and the optimal trajectory? Okay, so what do I do? Oh, come on, we've been talking about this for the last month. What do I do? What do I need to do? No. We've gone through all that. We don't start back at the beginning now, do we? We've done all that. What do I need to do? Yeah, I need to derive the first order optimality conditions for this optimal control problem, right? Which means I need to write down the Hamiltonian first. So what's the Hamiltonian? H is equal to what? Well, what is it? Lambda transpose F, right? Which is equal to what? Well, if you want to give these labels, this is F sub H, F sub V, and this is F sub M. So now what is it? It's going to be lambda sub H times F sub H plus lambda sub V times F sub V plus lambda sub M times F sub M, right? Which is equal to what? Well, it's lambda sub H times V plus lambda sub V times what? T minus D over M minus G, and then minus lambda sub M times T over C. Right? That hard? It's not hard, is it? Okay. So now, if I look at that Hamiltonian, what do you notice about that Hamiltonian? What's that? It's not an explicit function of time, right? So H is not an explicit function of time. So what does that mean? What does that tell me? H star is a constant. Okay? What else do I know? I know that the Hamiltonian at TF is equal to minus d phi dtf. Well, what's phi? it's minus h at tf, right? So if I take the partial of phi with respect to tf, what do I get? What is this? No. It's a partial derivative. It's not a total derivative. I get 0, right? So I get 0, which means that h star has to equal 0 because it's a constant and it's 0 at one point, so therefore it's 0 everywhere, right? So it's 0. So the optimal Hamiltonian is 0. What else do you know? Okay, that's true. That's not really the first thing I was looking for, but we do need it eventually, so we'll use it. But there's something more fundamental that I want to know. Tell me something else about this Hamiltonian. Yeah, so what if I take dH dt in this equation, do I get any information about the thrust? No, right? I cannot take dH dt and get any information about the thrust. So I have to apply what? I have to apply the weak form of Pontryagin's minimum principle, right? Because H is linear in the control T, right? So if I rewrite this, so let's rearrange this, okay? I'm going to rearrange H because let's get all the terms that involve the control in one place. I've got lambda sub H times V. Let's factor everything out. Minus lambda sub V times d over m. I'm just taking all the things that are not a function of the control. Minus lambda sub V times G. And then I've got plus lambda sub H times T over M. That's this term right here. And I've got minus lambda sub M times T over C, which is equal to lambda sub H times V minus lambda sub V times D over M minus lambda sub V, well, put it all together. Lambda sub V times D over M plus G. That's those terms. And then I've got plus lambda sub H over M minus lambda sub M over C, the whole thing times T, right? That okay with everybody? What's that? Lambda sub H, lambda sub M. Where's the problem? It is lambda sub V. Here. Which one should be lambda sub V? Oh, sorry. Okay? I have all this written down here so that if I get lost, I can figure it out. Yeah, that's right. Okay. So now how am I going to figure out the optimal control? So how do I get the optimal control? Let's look at this. I can't take dH dt and set it equal to 0. It doesn't give me any information about the control. What's the next thing? You have to do this in sequence. What's the next thing I do if dH dt doesn't give me any information about the control? Now I have to apply the weak form of the minimum principle, right? So what I need is T star. T star is going to equal the argument of the minimum of T, which is now a function of, it's between 0 and T max of H, right? So if I look at that, I say, well, okay, what are the possibilities? So let's look at the possibilities. So T star is going to equal some possibilities. What happens if lambda sub V over M minus lambda sub M over C is negative? Then what's the optimal control? What minimizes the Hamiltonian? What's that? Right. So it's going to equal T max if lambda sub V over M minus lambda sub M over C is less than 0. Now I'm going to skip a little space here. What happens if lambda sub V over M minus lambda sub M over C is greater than 0? Then what happens? It's equal to 0, right? So it's equal to 0 if lambda sub v over m minus lambda sub m over c is greater than 0. Now what happens if lambda sub v over m minus lambda sub m over c equals 0? Now what's the optimal control? You don't know. It could be anything. I have no idea what that is right now. This is the singular arc. Because I have no idea if this condition is met over some segment of time, right, where this is exactly 0 over some segment of time, what the optimal control is going to be, right? If I have a segment, and that is a possibility, it could actually be that over some segment, this thing is exactly equal to 0, right? There's no way for me to know ahead of time right now whether or not that's possible, or whether or not it's true, right? I have to go through and I have to do some more work. Let's derive the costate equations, because the costate equations we still have to derive. So the costate equations are that lambda sub h dot is minus h with respect to h. So what happens if I take this with respect to h? What do I get? Remember, d is a function of h. So what do I get? Well, what do I get? I get the partial of d with respect to h, and I've got 1 over m times lambda sub v. What happens if I take lambda sub v dot? It's minus h v. What do I get? Take the derivative with respect to v. What do I get? You get minus lambda sub h. That's the first term, right? And then I've got everything in here else that's a function of v, which is only that thing right there. So I get plus 1 over m, the partial of d, with respect to v, times lambda sub v, right? And then I've got lambda sub m dot is minus hm, which is equal to t minus d over m squared times lambda sub v. Okay, it's the only place that m occurs. Okay? Yeah? Now, if this is the case where I am not sure what the control is, right? Because the other two I know what the control is. If this is true or if that's true, then I know the control is going to be max or min, right? But in the middle, I don't know whether the control is going to be max or min. So the condition is, this is the singular arc condition. So the singular arc condition is that thing over there, lambda sub v over m, minus lambda sub m over c is equal to 0. Which, if I rewrite this, what do I get? I get c lambda sub v minus m lambda sub m is equal to 0, because if I put this under a common denominator, the mc drops out, right? Because m can't be 0 and c is not 0. Okay? So I get that condition right there. So if you look at that, let's suppose I define that condition as I. Call this thing I. So if this condition is met, I'm on the singular arc, right? So how am I going to determine the control? This is not a function of control. You see that it's not a function of control? Do you see that? Or do you not see that? Right? Because none of these is a function of control. I don't know what any of these things is, right? When I say a function of control, I mean an explicit function of the control. It's not, right? So let's take I dot. So what happens if I take I dot? I dot is equal to what? C is a constant. So I get C times lambda V dot minus M dot times lambda M minus M times lambda sub M dot. Okay. Now, if you substitute in, you get C. Now, what's lambda sub V dot? We've got it sitting over here. lambda sub v dot is minus lambda. Can somebody read it to me? Somebody read it to me? Lambda sub v dot. Minus what? 1 over m.
Lambda.
That's it? Okay, so that takes care of this. And I've got minus m dot, so plus, I've got m dot, which is t over c times lambda sub m. And I've got minus m times lambda m dot. What's lambda m dot? T minus d over m squared, right? Lambda v. Right? So I dot, if I rewrite this, I've got minus c times lambda sub h plus c over m partial d partial v times lambda v. And I've got plus t over c times lambda m. And I've got minus t over m times lambda v. And I've got plus d over m times lambda v, which is equal to minus c lambda h plus c over m partial d partial v times lambda v. I'm going to move this thing out front. Minus t over m lambda v. And then I've got, so if I look at this together, what do I get? I get plus, I've got t times m. Let's factor it out first. So I've got lambda sub m over c minus lambda sub v over m. The whole thing times t, and I've got plus d over m times lambda v. Now you can look at this right here, and you can see that it's the same thing that I had over here. It's just the negative sign of it, right? So this, if I put this whole thing together, what do I get? This is equal to lambda sub m times m minus lambda sub v times c, all divided by c times m. So if I look at this, I've got the same thing as I've got here, except for I've got a negative. So this whole thing is 0. So, because it's equal to I, and I is equal to 0 on the singular arc. So now let's look at this condition. So if you look at this condition, you'll see that I dot is equal to minus c times lambda sub h plus c over m, the partial of d, with respect to v times lambda sub v. And then I've got plus d over m times lambda sub v. So if I look at that condition, what do I know about this? What do I know about I dot? What does it have to be on the singular arc? No. What's this? What's I on the singular arc? 0. So what's I dot on the singular arc? It's also 0, right? So this whole thing has to equal 0. Is this a function of the control? No, it's not a function of the control either, right? So you have to differentiate it again, right? I'm not going to differentiate it again, all right? If you differentiate this thing one more time, if you take I double dot, it just gets really crazy algebra. If you take I double dot, you'll find that I double dot is an explicit function of t. And so therefore you can actually solve for t, and you can put that in on the singular arc. Now, you have to have a way of being able to figure out where the singular arc stops and where the singular arc starts. Okay? So that's the next thing we're going to do, is we have to figure out that. I don't have enough time to be able to do that today. I thought this was going to take me less time. So the next lecture, we're actually going to figure out the last condition is we have to, because in order to do this, let me just draw a picture here, right? So I've got a problem where let's just this problem is actually should be fairly clear that when you start, you have to fire at Tmax, right? If you fire 0, you're not going to get off the ground, right? So you're going to be at Tmax. And then at some point, you're going to switch to over here to 0, right? Because at some point, you're going to turn this thing off. in between, this is the singular arc. This is T here. So I have to know where the singular arc starts, right? So this is the start of the singular arc. Because if I don't know where the singular arc starts and I don't know how long it goes for, I have no idea of knowing when to change my optimal control from a max to whatever it's going to be on the singular arc, right? So this part of the trajectory right here, we have to have a beginning point and an end point in order to be able to figure this out. So this is the end of the singular arc. So what I'm going to do next time is I will derive the conditions for the start and the end. But now, wait a second, I'm not done, okay? I hope you're starting to get an appreciation for how difficult this gets, right? You're seeing that we're putting together this theory. So we've derived these optimality conditions. We say, okay, well, if all is good, and I don't have to worry about, bang controls, then I can just take DHDU and set it equal to 0, and then I can derive all my other optimality conditions, and boom, I've got a set of optimality conditions from which I can determine the optimal trajectory, or an extremal trajectory and the extremal control. But there's one kink in there. What happens if the optimal control doesn't occur at the interior? Now I have to deal with the second possibility, which is that I have to deal with whether it occurs at one extreme or another, depending on if the Hamiltonian's linear in the control. But now there's even a third possibility, which is that even if the Hamiltonian is linear in the control, there's a possibility that it may not be the case that the optimal solution is min or max. It may actually be something in between, because there may actually be a presence of a singular arc. So you can see that if I have a general problem, and I have no idea if it's very complicated, I've got like math, like lots of math sitting on a page. I have no idea whether I'm in one case, whether I'm in another, and if you're going to go through all this analysis, it could take you an extremely long time and a lot of effort in order to be able to extract the feature that you're trying to see if it's there or not, because it may not be clear at the beginning that it even exists, right? So the fact that this even is possible is in and of itself a problem. If it actually turns out that it is really the case that there is a singular arc, now let's take this problem before I finish class today. Let's take this problem and imagine the following scenario. Imagine the scenario where I don't just have one singular arc, but I've got multiple singular arcs. I go off a singular arc onto a singular arc, off a singular arc back onto a singular arc, off a singular arc back onto a singular arc. And I may do that many, many times. And if I have a process that goes over a very long period of time, I may be switching back and forth between singular arcs and non-singular arcs across the entire trajectory. You can see this is going to be a really painful thing to have to figure out where all the singular arcs are, right? So this is a very difficult thing about optimal control, is that even simple problems lend themselves to having extremely complicated solutions. This is not a complicated problem. I'm just firing a rocket off the ground and having it go straight up in the air. All I want to do is get to the highest altitude I can. How much simpler a problem can you think of than that? You've done this before, right? You take a ball and you throw it way up in the air, right? I mean, it's a very normal problem that people experience every single day in like sports or whatever it is, right? I mean, it's a normal thing. Yet it has this absolutely pathological solution associated with it. So if a problem this simple has such a pathological solution, you can imagine that if I have a real physical problem, it's going to get even worse. All right, which is why we can't do these things generally mathematically. But you have to establish the theory so you know what to look for when you actually start doing things numerically. So the next class, what I'll do is we'll derive these conditions to give you an event constraint that allows you to be able to figure out the start of the singular arc. And then I'm going to talk about one or two other theoretical constructs, and then we're going to move our way into nonlinear optimization, which is the next topic in the class. Okay. So my main point to this lecture was to identify that singular arcs are difficult to deal with, and you have to know like what you're looking for in order to be able to